Imagine you have a brilliant student who aces every practice test but struggles on the actual exam because they have memorized the answers instead of truly understanding the material. In deep learning, neural networks can do something very similar. They can become too specialized to their training data. This challenge of overspecialization is where dropout regularization comes in. Dropout is a powerful and widely used technique in deep learning designed to prevent neural networks from overfitting their training data by temporarily omitting or dropping out units from the network during the training process. So, how does this work? During each training step, Dropout randomly selects a certain percentage of neurons in a layer and temporarily sets their output to 0. It is like training a different, thinned neural network at each iteration. This random disabling of neurons forces the remaining active neurons to learn more robust features that are not overly reliant on any specific set of inputs or particular co-adaptations among neurons. Think of it as forcing your network to learn multiple independent ways to solve a problem. This technique effectively makes the model more generalizable. This process creates an ensemble effect. Instead of explicitly training many different models and averaging their predictions, Dropout implicitly trains an exponential number of thin networks that share weights. When it comes time for prediction on new and seen data, all neurons are present, but their outgoing weights are scaled down by the dropout probability to maintain the expected output magnitude from training. This ensures that the network is consistent between training and inference. To implement dropout, you typically add a dropout layer after some of the fully connected or convolutional layers in your network. You specify a dropout rate, often represented as p, which is the probability of a given neuron's output being set to 0. Common values for p range from 2/10 to 5/10, with 5/10 being a frequent choice for hidden layers. Experimenting with this rate is key to finding the optimal balance for your specific model and dataset. What makes Dropout particularly ingenious is its simplicity and computational efficiency. It achieves significant regularization benefits without needing to modify the objective function, add complex penalty terms, or train multiple separate models. It is a plug-and-play method that has become a fundamental component in almost every state-of-the-art deep learning architecture because of its consistent ability to improve generalization. By randomly introducing this element of uncertainty during training, dropout regularization compels your deep learning model to develop a deeper and more distributed understanding of the data. This ultimately leads to models that perform for better on new and seen examples, ensuring that your network truly understands the underlying patterns rather than just memorizing the training set.